Hello, I'm Tahmineh Lohrasbi, the reporter of question number 5, synchronized candles. Oscillatory flames can be observed when several candles burn next to each other. Two such oscillators can couple with each other, resulting in in-phase or anti-phase synchronization, depending on the distance between set of candles. Explain and investigate this phenomenon. Okay, here's my approach. First of all, I will show you my explanation, how the flames work simply, the types of the flame, and the relevant parameters. Second, I will show you my experiments and the analysis of them, and frequency of the flame and intensity of flame's convection. And at the end, I will conclude my presentation. Okay, explanation. How do flames work? At first, there is a hot air that causes the convex to burn. So, because of the capillary action, it moves up and the flame burns. At the left, as you can see here, we have the fresh of air that comes to the flame, and at the end, because of some chemical reactions, you can see that the carbon dioxide, carbon monoxide, and the water will exit from the flame. And at the top of the flame, there is hot air and low density, but as time passes, it gets colder and colder, and because of the convection flow and gravity, it will comes down. So we call it convection. Here we have radiation because every hot thing has radiation. Okay, as you can see in some videos of in-phase mode and anti-phase mode, as the question mentioned, we can see that the flames merged. But why and how? We can answer this question with these two actions, the convection flow and Bernoulli. The convection flow of these two flames causes the coupling here because the pressure will increase at the sides of the flames and in the middle of the flames because the pressure decreases and the actual temperature increases and pressure decreases and velocity increases. You can see the Bernoulli. So they merged, as you can see in some videos and my experiments. Okay, here is the types of behavior that we observed from the flames. First, it is a stable flame. As you can see, it has small oscillation. And death mode, it is same as stable, and it has also a small oscillation. So we ordinated these two types in one part that we call it no oscillation. And next mode is in-phase mode, as the question mentioned. As you can see, uh, the the flames merged and have same oscillation, and the delta phi is equal to 0, and we can see no phase differences. And the next mode is Mexican wave mode. As you can see, it is same as in-phase mode, but with high amplitude, as you can see here. We called it coordinated oscillation. The 5 is anti-phase mode. The delta phi is equal to P, and they're vice versa. And the number 6 is synchronized mode, that it has disorders. We we call them uncoordinated oscillations. Okay, here's the relevant parameters. As you can see, the number of the flames, distance, layout, and the flame are very important in these experiments. And next one is the material ones, material parameters, that we can see the wick thickness and the paraffin and other sources can cause this phenomenon, some differences. Okay, here's my experiments. The conviction have two main parts. That first one is the windproof, because windproof causes disorders in the flame, so we should do these experiments indoors. The next one is the distance between the candles, as the question mentioned. The 80 millimeters and 40 millimeters, we used our experiments, but in the more than that or smaller than that, they merged or they have no selections. I will show you my experiment so we understood it better. Next one is the another methods for capturing video, because of we should have specific parts of the flame, actually the the flames of the candle, so we should use dark background and special methods of camera. Okay, here's is the differences between the distance of the candles. As you can see, in 50 millimeters and 10 till 10 millimeters, you can see no effect, but in 90 millimeters, you can see small flickerings. But fortunately, in 80 millimeters, we are successful and we can see in some big oscillations. But in 7 millimeters and smaller than that, we usually see that they merged. Okay, it is my first observation that I tracked the tip of the flames, and you can see they had coordinated oscillations in 80 millimeters and two candles. Okay, when we track that, we use the Fourier transform to see the peak frequency, and as you can see, the part A and part 2, they're all similar, as you can see in the peak frequency, so we called it in phase mode. So the analysis of the setup tells us that because of the same volume of the fresh air enters from all sides and it is symmetric, we see in phase mode. Uh, this experiment is same as before, but the only difference is because of the numbers of the strands. As you can see, the left part has two strands, but in right part you can see only one strand. But it is interesting to say that this difference causes these flames to oscillate in disorder modes. So the two we can say that because two flames makes more heat and they burns faster and stronger, you can see disorders. So it causes disorder in the shape of the flame, and we can see anti-phase oscillations. Uh, mm, this coordinate oscillation, sorry. In experiment setup number 3, I changed the height of that and their difference in the height. As you can see, they have anti-phase mode, and because the difference in the height causes difference entering volume of the air, we can see that they are we have anti-phase mode. Okay, the comparison of these setups tells us that disorders causes uncoordinated oscillations, but if the entering flow is similar, we can see coordinated oscillation or infinite. Okay, because the question says that several candles burn next to each other, it means more than two. I put three candles next to each other, but it increases the distance. So I cut the paraffin. As you can see, it causes some less accuracy. So I made three models of candles by myself in two distances, 80 millimeters and 40 millimeters. Also, the number of the flames is important, so I increase the number of the flames. As you can see in 2, 3, and 4, you can see small oscillations, but in 5 numbers of the flames, you can see better oscillations. Layout design. Okay, I make three layouts, and the first one is a pentagon shape, the second one is a line shape, and then it is a combinations of these two layouts that I called it trapezium. Okay, I started my experimental setup. Okay, first of all is the shape of the pentagon in 80 millimeters. As you can see, it has in phase mode and Mexican wave mode. I track the video and uses the positions of the tips of the flame, and then I used a Fourier transfer to see the peak of the flames for each 5 tips in this video, and then as you can see, they're all same, and the numbers of the frequency are same, so we called it in phase mode. Next one is that shape in pentagon, I mean, in 40 millimeters. They merge, so they have in phase mode. The answer the setup tells us that because the same volume of the air enters from all sides, So we have symmetric oscillations, and specifically here is in phase mode. Next one is the line shape that in 80 millimeters. As you can see, mostly it is stable mode. In 40 millimeters and line shape, we can see they merged and they have in phase mode. The annals of the setups tells us now that the two sides of this shape have the volume of the fresh air from three sides, but in three candles in the middle we can see they have the fresh air from only two sides. So the two flames in the sides of this shape they're stable, but in three candles in the middle have less fresh air and they have coordinated oscillation, so they have in phase. Next one is the trapezium shape in 18 millimeters. You can see it has oscillations in stable form and in phase mode. Stable and in phase mode. In 40 millimeters it is like before, but because they merged you can see in phase mode better. So the annals of this specific layouts tells us that because it is the combinations of pentagon and line form, for the line side it wants to be stable, but because it is also a shape of pentagon it wants to oscillate like in phase mode. So it is the combinations of the modes because it is a combination of the layouts. I changed the wick also, that as you can see it melts faster and it melts the more candles melts and it generates more soot and smoke. So because of that you can see Mexican wave more than before. I also changed the materials of the candles, as you can see, but actually it doesn't change the essence of the phenomenon. Again, if you change the source of the candles, you can see in phase mode again, so it is also have no specific differences in this phenomenon. So it is the conclusion. The stable flame. Airflow is symmetric in the single flame arrangement, so we have a stable flame. In phase mode and Mexican wave mode, because they have the same fresh of air entering from all sides, so if the temperature increases, the velocity increases, the pressure decreases, and you can see that the flame drags down. But again, because the fresh air enters from the sides, the flame elongated. But the only difference between in-phase and Mexican wave mode is because it melts faster and it has high frequency, we call it Mexican wave mode. In death mode, when we see that the flame shape is long and slender, so we call it death mode. And also because in the middle we can see the rising hot air, the shape of the flame is like that. Also, the other shapes are anti-phase mode and desynchronized mode. That because there is a different temperature in the two sides, as you can see in the left part, as I said before, it is the two strands and the right is one strand. You can see disorders in temperature and pressure actually. So we have asymmetric flames and uncoordinated oscillations. So in my experiments, I observed that there's 5 important parameters that causes these modes. That the first one is the fresh air, the second one is temperature, and the other is the distance in the layout. Again, it is the hot air and the light gases that exist from the middle of the candles. And next one is convection. Here, if you increase the number of the flame, increase the hot air and the convection speed. If you change the distance in 80 meters, you can see the oscillations, but in smaller than that, they merge, and bigger than that, you can see that they had no oscillations. If you change the layout, you change the volume of the fresh air, and again you change the oscillations. And if you change the level of the flames, you change the temperature and change the pressure, so it is finally difference in the phase. But if you change the material, actually the wick thickness and the paraffin or other sources, we can see there is no difference in the essences of phenomena. Okay, here's my references, and thank you for your attention.